Entropy. In short, entropy is the average information from a process. It really doesn't make sense to talk about averages of things like probabilities, but information is measured in actual units, in particular bits, and therefore it does make sense to talk about average information, which is going to be called entropy. So if x is a variable associated with a finite set of outcomes, then the entropy, denoted by h of x, is the average information in the outcomes of x over n trials as n becomes arbitrarily large. Just like when we define probability, only now we're defining entropy as average information as n goes to infinity. So the entropy in a toss of a fair coin is 1 bit because all outcomes are 1 bit in length. So if we were to toss the coin n times, then the result could be encoded, or all possible results of n coin tosses could be encoded into n bits of information. If we rolled an 8-sided die, then all the outcomes could be encoded with 3 bits. We've already shown that. So if we roll the 8-sided die n times, then all possible outcomes would be encoded into 3n bits of information, and therefore the average is 3. So let's look at information for a process. Let's look at toss of a fair coin. So we've already shown x greater than 0 is either 0 tails or 1 heads. So there's 1 bit of information from tossing a fair coin because 1 single binary digit suffices. And what this means is if we were to look at observations over n trials, the average would be 1 bit. So no matter how many times we did it, on average we would only need n times 1 bits to encode all the possible outcomes of the n trials. So entropy is average information. This is actually a familiar idea. If there are 2 to the b outcomes in S for some integer b and each outcome is equally likely, then each outcome can be encoded as a string of length b. N trials produces bn bits of information, and so therefore the average over n trials is just b. But what if there are not 2 to the b outcomes? So for instance, what if we had a spinner and we had 3 possible outcomes? Well, in this case we could use a tree for 1 trial where x greater than 1, that's a 0, and x greater than 2, that's either a 0 or a 1. And you'll notice we have 1 spin has 1.67 bits on average. But we need to do this average over n trials as n becomes arbitrarily large. So notice that 2 trials would have 9 outcomes. So trial 1, we would have 1, 2, or 3. And trial 2, we would have 1, 2, or 3. And we could create a tree for each. And if we did so, then the average would still be 1.67 bits. But this is not the shortest encoding. Not the encoding requiring the fewest bits. Remember, information is the length of the shortest string that can represent all possible outcomes. So in order to see that there is one shorter, let's just take all the possible pairs from the 2 spinners. So spinner 1 will be first, spinner 2 second. And now let's, as best as possible, split this into 2 groups. And then let's define a condition that separates those 2 groups. And then each of the 2 groups will split those again and in as balanced a way as possible. And then the remaining groups will split in as balanced a way as possible, each time writing down a condition that corresponds, the true-false actually corresponds to this subdivision. And when we get done, we'll have something that looks like this. So let's look at what we've got. 7 of these outcomes require 3 bits. 2 of the outcomes require 4 bits. So the average over the 2 trials is 7 times 3 plus 2 times 4 over 9, which is 1.611. And that's less than 1.67 that we saw on the last slide. So now we know the average information is no more than 1.611. This is for 2 trials. For n equals 3, we would get even fewer than 1.611. And in particular, if we keep going, we'll find that the log base 2 of 3 is 1.5849 bits. In other words, 1 trit is 1.5849 bits. And here's how it works in general. And this is for m equally likely outcomes. We take our balanced tree and apply it to m to the n possible results for the n trials. And then we represent each of those outcomes as the leaves of a tree. So we have m to the n outcomes over the n trials, and because we're using a tree, we have approximately log base 2 of m to the n bits to encode all the possible outcomes over those n trials. The entropy with m equally likely outcomes is the average information, which is approximately the log base 2 of m to the n divided by n. And so therefore a process which produces m equally likely outcomes has an entropy of log base 2 of m. So if each outcome is equally likely, then the entropy is the log base 2 of m, which is the negative log base 2 of 1 over m, and that's the negative log base 2 of the probability of these m equally likely outcomes, and that's the self-information. So if all the events are equally likely, the entropy, the average information, is just the self-information for each of the individual outcomes. So let's look at, say, a 6-sided die. We have to make decisions. So our first decision is x greater than 2, and then x greater than 1, x greater than 4, and then x greater than 3, x greater than 5, and this encodes all 6. And notice that some of these require 2 bits and some require 3 bits, so therefore we now know that the shortest encoding is going to be somewhere between 2 and 3 bits, and in particular the entropy from the roll of a fair die is 2.58 bits, which is a little more than 2.5. So if we toss the 6-sided die n times, then all possible outcomes could be encoded into approximately 2.58 n bits of information for an arbitrarily large n, as n goes to infinity. So entropy is average information. But you still might be asking, where did the 2.58 come from? Well, there are 6 outcomes from rolling a fair die, and the entropy is the log base 2 of 6, which is the 2.58496. But even more pertinent, you might be wondering, what if all the outcomes are not equally likely? Well, it turns out the balanced tree encoding still works. We just have to be careful how we talk about the averages. And we're going to obtain a more general form for entropy, the one we'll be using the most in this course, and that is it's going to be the sum over the probabilities times the self-information, or the expected value of the self-information. Now, to show you this is the same, notice that if I of x is the log base 2 of m for all x, so we have m equally likely outcomes, then this special form, the sum of the probabilities times the self-information, can be written as the following. And because the log base 2 of m is constant, doesn't depend on x, we can factor it out, but the sum of the probabilities is 1, and therefore we get the log base 2 of m, which is just the self-information. So truly this formula does generalize what we've already seen. So how does the balanced tree encoding work for when you don't have equally likely outcomes? Well, it's the same reasoning process we've used already. We apply the balanced tree to the m to the n possible results. We get our tree again. We've got our m to the n outcomes over n trials. And the key here is that the outcome O sub x occurs about p of x times n times. So because they're not equally likely, they occur with different frequencies. The information from O sub x, as we've seen, the self-information is the log base 2 of the probability. That should actually be negative log base 2 of the probability. So we get self-information for 1 occurs about probability 1 times n times, so on and so forth. You add those up, take the limit as n goes to infinity, and you get our special form. So if outcomes are not equally likely, the balanced tree approach is essentially what's called the Shannon-Fano encoding algorithm, and it simply is a way of allowing the extension of ideas for 2 to the b equally likely outcomes to be generalized to any m and to not equally likely. Now the other thing is, if you're not clear about information entropy, then just use this balanced tree approach to make sense of what you're actually looking at. So what we've shown is that the entropy is the sum of the probabilities times the self-information. That's actually the expected value of I. And we saw that it's equal to this sum of p of x, the log base 2 of p of x. And h of x here is the expected surprisal, or the average information produced by values of an experimental variable over arbitrarily many trials of that experiment.